Okay, in this video we are going to revise SC13, which is on the transition metals. It's a triple only topic that you would have done at the end of year 10, but obviously it wasn't on your mock, so I'm assuming you've forgotten all about it. When we're talking about transition metals, we're talking about this group of metals here in the center of the periodic table. So they're not in your traditional groups 1 to 0, it's just this central block here. And of the transition metals, the one you probably are most familiar with would be iron, copper, zinc. They're the ones that seem to come up the most often. You need to be able to describe their physical and chemical properties of the transition metals. So if we start with physical properties, they have got really high melting points. Okay, so for reference, we learned that group 1 were relatively low. So you see here sodium 98, aluminium's your typical metal 660, and then copper, a transition metal, 1085. So yes, group 1 is relatively low, but even compared to aluminium, these guys have very high melting points. One of the other transition metals, tungsten, has a melting point over 3000 degrees Celsius. So even as metals, they have very high melting points. Other thing you need to learn is that they've got high densities. So again, group 1 metals had low densities. They floated on the surface of water, but you drop copper into water and it's going to sink right to the bottom, and that's true for your other transition metals as well. Other properties will be like conduct electricity, and they're malleable, so they've got those typical metal properties, but the ones you really need to know are high melting point and high density. Chemical properties then is how to do what they react, okay? Because they're not in one of the traditional groups, we don't know if they're going to lose 1 electron or lose 2 or lose 3, but what we do know is that when they form compounds, they are going to be coloured. Your classic example that we met last week, or sorry, when we did electrolysis, is copper sulfate, which is a blue colour. The copper ions, the Cu2+ ions, are blue in solution, and that's not just copper. Your iron ions have different colours as well, and it's a property of the transition metals, a chemical property. They form coloured compounds. They can also be used as catalysts. All right, remember, we use catalysts to speed up a reaction. They lower the activation energy. You get a higher proportion of successful collisions. Classic example is iron is used in the production of ammonia. We'll study ammonia in more detail when we look at equilibrium, but iron is a transition metal and it's used to speed up this reaction. Next thing we're going to look at is just corrosion. Alright, so corrosion, I've got an example of corrosion here. I've got iron reacting with oxygen and forming iron oxide. And the reason this classifies as corrosion is because your product is weaker than the starting metal. And that's what corrosion is. When it reacts with something in the environment, typically oxygen, and forms a product that is weaker than the starting metal. So obviously this isn't a good thing, okay? We don't want our iron to rust, we don't want it to become weaker. So how can we prevent this? Well, one thing we can do is we can stop it reacting with oxygen by protecting it from oxygen. If I store my metal in something like argon or nitrogen, these two gases are very unreactive. So argon is in group 0, full outer shell, doesn't need to gain or lose electrons. Nitrogen, if you remember, has got a triple bond between those two nitrogen atoms, very difficult to break, so also very unreactive. Your other option is to just coat your metal in paint or oil or grease, or just something that will stop the oxygen getting to it. And then this last one here, it's known as sacrificial protection. But if you take your metal, just say it's iron, and you attach a more reactive metal, so thinking to your reactivity series, any metal more reactive than iron. So if you stick bits of aluminium or bits of magnesium onto your iron, then the more reactive metal will react preferentially over the metal you're trying to protect. It's called sacrificial protection. Other thing you can do to prevent rusting specifically, so here in my equation I've just got iron and oxygen, but water is needed for rusting as well, so it's not just oxygen, it's water. So you could really add water into your equation there, right, plus water, and your product would be hydrated iron oxide, which you don't need to know the formula of. It's just iron oxide with kind of water molecules attached to it, but you do need water, and a way to protect from water is using something called desiccant powder, and what that will do is absorbs water vapor from the air and stops your iron rusting. So that's an example of the corrosion of iron. Okay, other transition metals will do the same thing. They'll react with oxygen and they'll form a product that is weaker, therefore they're deemed to corrode. But there's some metals that react and don't corrode, and a classic example of this is copper. Okay, so the Statue of Liberty is made of copper. Okay, and copper is a brown colour, but if anyone's ever seen the Statue of Liberty, you'll know that it's green, and the reason is the copper in the statue has reacted with oxygen, but it didn't become weaker because you built up an oxide layer all around the Statue of Liberty, a green oxide layer that protected all of the copper within. So the outside layer reacted, formed an oxide, which is why it looks green, but that outside layer prevents the rest of the copper within from reacting. So overall it's not getting weaker. It's changed colour, so it's got a different appearance, but it's not getting weaker. If I compare that with iron, it's not just the outside of iron that will start to rust. It will the whole metal will start to rust and it will start to crumble, so it does become significantly weaker. So this is called forming a tarnish. Oxygen's a classic example, copper is a classic example of a metal that forms a tarnish. Right, I want you to press pause and just do questions 1 to 5 on page 39. Alright, physical properties. If they don't specify saying malleable or conduct electricity will get you the marks, but often they give you, one of those multiple choice questions and you have to pick out the relevant properties, so just make sure you know they've got very high melting points, very high densities, even compared to other metals. Chemical properties, they form coloured compounds, copper sulfate being blue, classic example, also used as catalysts. Corrosion, when a metal reacts usually with oxygen and becomes weaker, so it forms something that is weaker than the original metal, is said to corrode. Obviously if it's reacting with oxygen, you can also describe this reaction as oxidation. Rusting is a special name for the corrosion of iron, just as the most common example. You need oxygen, you need water, so both of them are just coming from the environment and they're making the iron weaker. If I want to prevent the rusting, okay, I can coat it in paint, that will stop it coming in contact with oxygen. I can attach a more reactive metal, okay, so sacrificial protection, or I can store in an inert atmosphere, an unreactive atmosphere, maybe argon or nitrogen. I could also use desiccant powder to absorb any moisture from the air. How does sacrificial protection work? So attach a more reactive metal. So if it was iron I'm trying to save, I'll attach aluminium or magnesium. Typically I wouldn't be attaching things like sodium or potassium just because they're rarer and not as easy to handle. I attach that more reactive metal, and then that more reactive metal will choose to react with the oxygen instead of the metal I am trying to protect, and that will protect it right up until the reactive metal has run out. Okay, so eventually that protection is going to wane. Whenever your reactive metal has fully reacted, then your other metal, your iron for example, will become vulnerable. Alright, next up we've got electroplating, which is a nice extension to the work we've been doing on electrolysis. What electroplating is the use of electricity to cover one metal in a thin layer of another metal. So electro again implies electricity, plating one metal in a thin layer of another. So why would you want to do this? Reason one, to make something more attractive. All right, so if you've got some cheap jewellery and you want to make it look nicer, you might not be able to afford a full gold ring, but you could have a cheap copper ring and just coat the outside in gold so that it looks nicer, so it'll improve appearance. We do that with cutlery as well. It's rare that you'd have solid silver cutlery. You'd have a cheaper metal and you just coat the outside in silver, so it looks a little bit nicer. It can also prevent against corrosion. So a classic example of this is we use steel often to make things, but steel contains iron, and as we've just seen, iron can rust. So if you coat your steel in chromium, when it reacts with oxygen, it forms a tarnish. So your steel, which contains iron, is protected, and your chromium around the outside will form a tarnish. But in order to get that chromium coating over your steel, you're going to use electroplating. So how exactly does it work? All right, so this is my little setup. Okay, so let's say, for example, I want to coat a copper ring in silver. Okay, I'm setting it up just like I would electrolysis. Okay, I've got my battery because I need to generate electricity. Positive is my anode, negative is cathode. At the anode, I have put my piece of solid silver, and we'll see why. And on the cathode, I have got my copper ring. Now, I want this ring to be coated in silver. Okay, and then I have got my electrolyte, which in this case is going to be silver nitrate, and you can see I've got it aqueous. So I'm going to describe what happens, and then it will make it hopefully a little bit clearer why I've put the silver at the anode and the ring at the cathode, and also why this is my electrolyte. So let's start by looking at what occurs at the anode. Okay, hopefully by now we know that at the anode you are always going to get oxidation. So something is going to have to lose electrons at the anode. Okay, and if we look at what we've got, okay, look at what our ions are. All right, to the positive anode I've got silver nitrate that contains the nitrate ion. So that nitrate ion is negative and will migrate to the anode. Okay, I've also got, because it's aqueous, I'm going to have OH minus migrating to the anode. And then at the anode as well, I've also got silver. So solid silver is what my anode is made of. So remember, if I was using graphite, it's unreactive, it doesn't get involved. But just like when we had copper at the anode, silver is reactive enough to get involved. So I've got three choices. Which one of these is going to be oxidized? It is going to be silver. Okay, so nothing happens to OH minus, nothing happens to NO3 minus. You can completely ignore them. It's silver that is oxidized. So to show that silver is going to be oxidized, I'm going to write myself a half equation. It starts off as silver, which is a solid. It's oxidized, it loses one electron, not two like copper, it just loses one. And when it loses an electron, it becomes silver with a positive charge. And just like we saw with copper, as soon as it becomes an ion, the state symbol will change. It is no longer solid, it is now going to be aqueous. And those silver ions that we are going to form, all right, so you're going to form a silver ion, and those silver ions are going to migrate over to the cathode. The positive silver ions that we're forming will be attracted to the negative cathode. Okay, so if we have a look at what's happening at the cathode, we know that if anode is oxidation, cathode is reduction. So let's have a look at what we've got at the cathode. Well, we're making silver ions. Okay, from the electrolyte we already had silver ions, so I've got some Ag plus from the anode, some Ag plus from the electrolyte. Also, because it's aqueous, I'm going to have some H plus. And all of these are coming over here to the cathode. And at the cathode, I've also got copper. So again, I've got three things: solid copper, H plus, and Ag plus. Now, reduction is obviously gain of electrons. Something has to gain electrons, all right? And you might zone in on the copper because that's what we've seen before. Okay, but remember, when we were reducing copper before, we were reducing a copper ion. Okay, Cu2 plus had lost 2 electrons. We gave it the 2 electrons back. But this is not copper ion. This is just copper. It is a metal, and metals do not gain electrons. So solid copper metal will not gain electrons. So your choice is between Ag plus and H plus. And when you're deciding, remember, you're using your reactivity series, and the least reactive is going to form. If you remember your reactivity series, you had hydrogen, below hydrogen you had copper, below copper you have silver. So it's right down here at the bottom. Because silver is a more stable product than H2, silver is going to form. So if I want to form silver, I'm going to have my Ag plus, my silver ions, which are aqueous. They've lost an electron, they gain their electron back, and it forms AgS. And what this will look like, okay, if you see by my state symbols, they're not ions anymore, it's becoming solid. And you are going to get solid silver deposited. Solid silver will be deposited around the copper ring, okay, which is exactly what we want. We want to improve the appearance of our copper ring by depositing this solid silver. For that reason, okay, because the silver ions are going to move towards the cathode, we're always going to put our copper ring, or whatever it is we want to electroplate, will always be at the cathode, because the positive metal ions will always migrate towards the negative cathode. So whatever you want to plate, okay, be it a ring, be it a fork, be it a bicycle, whatever you're trying to plate, that goes to the cathode, and the metal ions will move towards it. In terms of your electrolyte, okay, I'm using silver nitrate, okay, that's just because I'm trying to coat copper in silver, and I'm adding more silver ions to the mix. I don't want to have any other ions in there, okay. If I want to coat it in silver, I'm just going to use silver as my electrolyte as well as at my anode. All right, press pause again and have a go at question 6, 7 and 8. So what is electroplating? Use of electricity to coat one metal in a thin layer of another. Why do we do it? Improve appearance. You can also protect your metal from corrosion. If you want to coat a fork in silver, what you're going to do, silver is going to be your anode. Remember, oxidation occurs at the oxidation occurs at the anode. So I'm starting off with solid silver. It loses one electron to form Ag+. As soon as it goes into solution, as soon as it becomes an ion, it will go into solution, meaning it can migrate over to your cathode. Your anode will lose mass. At the cathode, you're going to have your fork. That's what I'm trying to coat. You've got reduction at the cathode. The ions gain back their electrons, become solid again, which is what you want. That solid silver is going to be deposited on the fork, and the cathode will gain mass. To get a nice kind of even plating, you just need to make sure your fork is nice and clean. Any bits of grease or dirt will stop the metal coating evenly. Aqueous silver nitrate is used as the electrolyte Y. So between silver and hydrogen, silver is lower on the reactivity series. If it's less reactive, it's more stable. So because it's more stable than the product H2, the Ag+ ions are preferentially discharged over the H+ ions. So you discharge the ion that leads to the most stable product. Most stable, least reactive, and that's going to be silver. Alright, last little bit, you've got alloys. So diagram on the left, I've got a pure metal, and you can see all of the cations are arranged in nice neat rows. So I'm saying cations because if you remember in metals, the atoms lose electrons to form positive ions, and then the negative electrons just become delocalized around the structure. And the attraction between the negative electrons and the positive ions is what holds the metal together. That's what a metallic bond is. So you can call these particles ions, although you will also see them called atoms, just because the electrons don't actually go anywhere. They don't leave the metal structure. It's not like they're going off to a non-metal. So you do see sometimes them being referred to atoms, sometimes them being referred to ions. More general term, particles. So all the particles here in my pure metal are the same size, they're in nice neat layers, and for that reason, if you were to take a hammer and hit the top row, it would just slide over the second row, and we can say that it is malleable. If you have an alloy is a metal mixed. Okay, so it's not a compound, it's a mixture. So it's a metal that's mixed with another element, or even more than one other element. And what you'll see here is I've got two particles of different size. And because they're different sizes, they disrupt my layers. And now if I take a hammer here to the left hand side, I'm no longer able to knock that top layer over because this particle here disrupts that layer. So what the alloy is doing, it's making it less malleable, which is making it stronger. Okay, so alloys are stronger than pure metals. They're less malleable. They're also less ductile. Ductile means can be drawn out into wires. Your classic example of an alloy is steel. So steel is iron mixed with carbon. There's a few different types of alloys of steel. They're called alloy steels. Classic example would be stainless steel. So in stainless steel you've got iron and chromium is around the outside of the iron, because chromium reacts with oxygen and forms a tarnish, so it stops the iron from being corroded. And because chromium's tarnish is colourless, you can see right through it and still see the shiny iron underneath. Another example would be tool steel. You mix iron with tungsten, that transition metal, with a really high melting point, and you form tool steel, which is so strong that it's used at the end of drill bits. So I've got questions 9, 10, 11. I'm just going to put under here. So what is an alloy? It's a mixture of a metal with another element. That word mixture is key. You have to say mixture. The other element doesn't have to be a metal. So classic example, steel is iron and carbon, and sometimes you've got two other elements mixed in there. Why are alloys stronger? So I've gone for ions here. So the ions are different sizes. If you've got an alloy and you've got two things mixed together, the ions will be different sizes. That disrupts the layers, and that means the layers can no longer slide over each other, and that's going to make it less malleable and therefore stronger. What are alloy steels? They're just different alloys of iron. You need to know that iron is the main metal in steel, so different alloys of iron, you're mixing it with different things, and depending on what you mix them with, they're going to have a range of different properties, some being stronger than other. I mean, you do need to know a little bit more about alloys than what I've written out for you here. It's in the information on in booklet D. It's just a little table with some common alloys and what they're used for. You'll see here when you go to do your exam questions, it did come up as a 6 marker one year. It's the only time it's come up, but yeah, it was for 6 marks. Compare and contrast the uses of pure aluminium and pure copper with alloys of them. So the pure ones are fine. You know, you can talk about you know, the size of the ions and the layers not being disruptive and all that, but you do need to know some examples of alloys of aluminium and copper, just so that you can give some uses. So you'll find that on the mark scheme. You'll also find that in your booklet D. So yeah, it's just stuff that you just have to learn off by heart. It's more of a cram job just before the exam. As long as you understand the idea behind it, I'm kind of happy for now.